Hello everyone, I'm Norman Wahlberger and thanks for joining me on this adventure towards understanding dynamics on graphs and how that develops a lot of exceptional structures in mathematics and physics. So we're taking the point of view that a lot of these exceptional structures that are occurring in Lie theory, in representation theory, but also in the standard model of particle physics and string theories, that a lot of these things are in fact explainable to a certain extent, at least, by studying graphs. The graphs, elementary though they are, generate this really interesting structure if we look at them from the point of view of the mutation game and the numbers game, which I'm going to explain in a few more videos. So these are relatively simple games that generate all kinds of interesting stuff. And my aim is to show you how a lot of exceptional objects in mathematics and physics arise from these games. So I've been telling you about the mutation game. We've had a little discussion about the symmetric group and different ways of thinking about that. Today I want to have a look at the output side of things, the exceptional structures. So I want to at least put some exceptional structures on the table so we can start thinking about where we're headed. And a really great place to start is with the Platonic solids, which actually play a very major role in this whole story. And a lot of things that we're going to be dealing with are sort of built up from the Platonic solids by going to higher dimensions and various variants. So the Platonic solids, well, there are 5 of them, of course. There is the tetrahedron. Okay, there is the cube. There is the octahedron. There is the icosahedron. And finally, there is the dodecahedron. All these models are made with a construction system called Polydron, which is quite pleasant. These things sort of snap together to form these things. So today what we're going to do is we're going to have an initial look at these things, especially with the view of understanding a little bit about their symmetry groups. So the group theory that's underlying here will be particularly important. And in subsequent lectures, we'll also look at some other algebraic aspects of these things. But our aim is to have a starting base to which we can go to 4-dimensional and higher analogs of these things, where things get a lot less familiar and a lot more complicated, but very rich. Okay, so we're going to count some things today, and let's start with tetrahedron, okay? First of all, let's count vertices, edges, and faces for all the Platonic solids. This is pretty easy. So this thing here obviously has 1, 2, 3, 4 vertices. The edges, well, let's say if we put it like that, there's 3 on the bottom triangle, and then there's 3 coming up here, so there's 6 edges, and there's 4 faces. There's that one, that one, that one, and that one. Okay, notice that vertices minus edges plus faces equals 2. That's Euler's celebrated relation. Okay, let's go to the cube. Well, the cube obviously has 8 vertices. It has altogether 12 edges. There's 4 on top, there's 4 on the bottom, and then there's 4 along the sides. And faces, of course, 1 on the top, 1 on the bottom, 4 around the middle, for a total of 6. And again, vertices minus edges plus faces is 2, as it should be. Next, the octahedron. Okay, the octahedron, in terms of vertices, well, there's 1 on top, 1 on the bottom, 4 around the middle, for a total of 6. There's 4 emanating from the bottom, 4 emanating from the top, and 4 around the middle, so 12 edges altogether. And number of faces, there's 4 around the top pyramid, 4 around the bottom pyramid, for a total of 8. And the icosahedron, okay, vertices, well, there's 1 on top, there's 1 on the bottom, there's a kind of a row of 5 along here, there's another row of 5 along there, so 6 plus 6, that's 12. And then to count the edges, well, maybe it's simpler to count the faces, okay? So in terms of faces, well, there's 5 on top, there's 5 on the bottom, and then there's sort of this strip in the middle, there's 10 of them, so altogether 20 faces. And then in terms of the edges, well, each face has 3 edges. So if we multiply this by 3, we get 60. But that's double counted the edge because each edge appears in one face. So we have to divide that by 2. So there's going to be 30 of them. And 12 minus 30 plus 20 is indeed 2. And finally, the dodecahedron, that has, well, maybe a little bit trickier to count them, but there's 20 vertices. There's also 30 edges, and there's 12 faces. So another way of getting that pretty easily is just by noticing that there's a close connection between the icosahedron and the dodecahedron, just as there is between the cube and the octahedron. So there's important duality that's happening here. The cube and the octahedron, these are dual in the sense, the following sense, that if you take a cube and you make a vertex at the center of each of the faces, then those points form an octahedron. And conversely, if you take an octahedron and put a point at the center of all the faces, then you get a cube. Okay? And that means that the number of vertices of one of these is going to be the same as the number of faces of the others. And that's also happening with the icosahedron and the dodecahedron. They're also dual. So if we put a point in the middle of each of the faces of the dodecahedron and join them all up, then we would get an icosahedron and vice versa. So we have these two kinds of dualities here. The tetrahedron is self-dual, in the sense that if you put new vertices at the center of the faces, there would be 4 of these, and then they would form another tetrahedron themselves. Okay, so now I want to talk about the symmetries of these things. And the symmetries are sort of two kinds. There is rigid motions, which are just things that you can actually do in physical space by taking a physical model of these things and moving it around. So what we're interested in is putting the object that we're interested in a particular position and asking what rigid motions can we make so that the object is mapped into the same position but possibly in a different fashion, like there, okay, or there. So a rigid motion in three-dimensional space turns out to be a rotation. So that's been known since Euler's day. So we're really talking about rotations of a tetrahedron that map the tetrahedron to itself. Okay, how many of those are there? Well, one way of thinking about it is to sort of think about where a vertex could go. Like, let's say we choose that particular vertex. Okay, if we're going to move this thing to some other position, then this vertex is going to go to one of the 4 vertices. And so there's 4 possibilities for where that distinguished vertex goes. But then to completely determine the resulting thing, we should also note an edge. So suppose that we choose not just a vertex, but also an edge emanating from that vertex, say that vertex and that edge. Then if we know, let me do it like this, so if I sort of put my finger along this distinguished edge, okay? If I know where the vertex and the edge are going, like maybe over here, okay, then that completely determines where the rest of it goes because it's a rigid motion, okay? If you know where this thing goes and you know this edge, then you know the whole thing. So there's 4 possibilities for where the actual vertex goes and 3 possibilities for where the edge goes, right? Once the vertex goes there, then the edge can go in one of 3 different edges emanating from there. So altogether 4 times 3, which is 12 different rotations of the tetrahedron. Now it makes sense to look at that a little bit more carefully. And if you haven't studied this before, it's really important that you gain some familiarity with these things. So I suggest that you get yourself some models of these things and actually think about the symmetries. Okay, it's really important. Every math student should spend some days at least thinking about the symmetries of the Platonic solids. It's actually quite a subtle business. So another way of analyzing what I just did is to think about the kinds of rotations that there are. So one kind of rotation is the simplest one, which is the rotation that doesn't do anything. Okay, the identity rotation. That is a rotation. So there's one of those. And then if we choose a vertex and have an axis through that vertex and the center of the opposite face, okay, we're talking about a rotation like this now. How many such possibilities are there? Well, there's sort of 3 possibilities. 1, 2, 3. Then we get back to where we started. But the first one, the one that doesn't move anything, we've already counted. That's the identity. So in terms of new ones, there's sort of 2 new ones that we get. Okay, so for every vertex, there's 2 sort of new rotations that can be generated through such an axis. So that's 8 more. So now we have a total of 9. And what other rotations are there? Well, if you think about it for a little while, you'll realize that the edges, the 6 edges, come in sort of opposite pairs. Like this edge here is incident with this one, this one, this one, and this one. It's incident with 4 edges, but it's not incident with this edge. So this is a pair of opposite edges that are not incident on the solid. And if you take the midpoints of those opposite edges, okay, then that's an axis of symmetry. And I can get a rotation that maps the thing to itself by essentially doing a half turn. I prefer to say half turn instead of 180 degrees. Half turn is more suggestive. Okay, so half turn sends the thing to itself. There's only one such rotation, which is not the identity, through such an axis. So how many such are there? Well, there's 6 divided by 2. That's 3 different such axes going through opposite edges. So 3 more rotations of that kind. So we had 1 plus 8 plus 3, that's 12. So we've sort of verified our count by counting the rotations in a somewhat different way. Now, what about all symmetries? Well, all symmetries. So all symmetries means that we're not just considering rigid motions, but also reflections. Okay, reflections. And a reflection doesn't, can't be illustrated with the actual physical model so clearly. So if I, let's say, did a reflection in this plane right here, then these 2 vertices are going to get fixed. But these 2 vertices are going to swap. Okay, so if I actually did that, I'd have to, sort of reassemble the whole thing. It's a map from the actual shape to itself, but not a preservation of the actual, tiles that are making it up. But it's still a symmetry of it. So we might ask, well, how do we count such things? Well, if I go back to the original way of counting, if I specify a vertex first and then an edge emanating from that vertex, then along that edge there are sort of 2 faces. In this case, there's the green face on this side and the red face on that side. If I choose one of them, let's say if I'm looking towards the edge, I'll choose the one on the right. Okay, so let's say that's going to be a specified edge. Now, in order to specify one of these generalized reflection type symmetries, or possibly involving reflections, I need to specify where the vertex goes. Maybe it goes up here. And then I need to specify where the distinguished edge goes. There's 3 possibilities for that. So 4 times 3 so far. And then the distinguished edge, let's say it was this one, this distinguished face here then, okay, has then 2 possible places where it can go. It can go where it is currently, or it can go to the opposite one. So I have to multiply by 2. Okay, so I get 4 times 3 times 2. So altogether, that's 24. And another way of thinking about that is it's just the symmetric group on 4 letters. Okay, that any permutation of these 4 vertices, just make any permutation, that's going to be a symmetry of the solid. So that's another way of thinking about what the whole group of symmetries of the tetrahedron is. So because the cube and the octahedron are dual objects, a symmetry of one of them is also going to be a symmetry of the other. So as far as symmetries go, we can just deal with one of them and we'll automatically deal with the other. So we're going to treat them both at the same time. Okay, so we're going to treat both of these at the same time. Okay, and let's see what we get. So let's start with or just look at the cube. Okay, so here's our cube. How many rigid motions or rotations does this thing support? Well, we can do the same kind of analysis that we did with the tetrahedron. We can think in terms of a distinguished vertex And of the three edges emanating from it, we can sort of choose one of those distinguished edges. Okay, so I'm choosing this vertex and that distinguished edge emanating from it. And now I'm claiming that if I have any rotation of it, it's completely determined by where the vertex goes. Like let's say I have it in starting in the standard position, okay? And there's my vertex and there's my distinguished edge. Now, all what I need to do is to specify where that vertex goes. Maybe it goes down here, okay? Down here. And I have to specify where the distinguished edge goes. I'll switch it a little bit so you see. So it can either, down here, it can either go along here, here, here. So altogether, there's 8 possible end places for the distinguished vertex, because there is 8 vertices. And then I have to multiply by 3, because then there's a choice of 3 possible places for the distinguished edge to be emanating from that new vertex. 8 times 3 is 24. So there's going to be 24 rotations. And it's a great exercise for you, if you haven't done this kind of thing before, is to sort of think more in more detail, what those kinds of rotations look like. The rotations are of different kinds. For example, there's the identity rotation. There's a rotation between, say, an axis through opposite faces like this, so I could rotate it like that. Or maybe I could do different things. Maybe I could rotate through an axis through opposite diagonals. Okay, so you can count, maybe there's other ones. So you can think about what those are. And now what about all symmetries, where we're not insisting that it's actually a physical motion, but just actually a mapping from the vertices to themselves that preserve the relations. So an easy way to perhaps get your head around there is to realize that in this case, if we look at the center of the entire cube, okay, the center of the cube inside there somewhere, okay, that the reflection in that central point is a symmetry of the cube, right? So that vertex there will be sent to the opposite vertex there. This point on top here will be sent to this point here. This point on this edge will be sent to this point on this edge, okay? So that kind of reflection is an orientation reversing map of the three-dimensional space. That means it's not a rotation of the kind we've been talking about. So basically, we can get at a whole new family of symmetries by taking any one of these 24 rigid motions and combining it with one of these reflections through the center. So in particular, if we take the identity and we follow it by reflection in the center, well, then we get reflection in the center. So that will be another symmetry. And so there's going to be 2 times 24 total number of symmetries when we include this reflection through the center and all things that you can get by composing regular rotations with that reflection. Okay, so we get 48 here. Okay, finally, let's look at the icosahedron and the dodecahedron. So remember, these are dual objects. So in terms of symmetries, I can deal with them at the same time, just as I did with the cube and the octahedron. So we're going to do those at the same time. That means we can only worry about one of them. Let's say the dodecahedron, which is everybody's favorite pretty well. Not everybody's favorite. The icosahedron also has some claim to being really the best one, but that's a debate, okay? Mathematicians are divided as to whether the dodecahedron or the icosahedron are more remarkable. Okay, so how are we going to deal with this thing? Well, we can do the same thing that we did before, so it's nice to have a sort of a systematic approach. So in these former cases, what I did is I said, okay, let's look at the vertices. In this case, with the dodecahedron, this one here, we have 20 vertices. Okay, so if I pick one of them, that one there, say, then I can also talk about a distinguished edge emanating from that. There's 3 edges emanating from that vertex. So I choose one of them, okay? And then I claim that any rigid motion of this thing, which takes it into the same position it was occupying before, is completely determined by where that vertex goes and where that finger goes. Well, let's say I'm going to move this thing up to here, okay? So I'm going to move it up to here, and I'm going to move this thing so that it's in this direction. So I'm going to do this. Okay? It's completely determined. Once I've moved this and I put this thing in the right place, then the rest of it is fixed. So how many possibilities are there altogether for that? Well, 20 places to pick a vertex, 3 for an edge, 60 is the total, 20 times 3. So there's 60 of those. And let me note that over here with the icosahedron, if we had done the same thing, the number of vertices for the icosahedron is 12. We picked one of those. But now there's 5 edges emanating from that, so I'd have to multiply by 5, and I'd still get the 60. Okay, and then what about all symmetries? Well, here, as in the cube octahedron story, reflection in the center of the entire solid is a symmetry. So if I imagine the center there, that vertex there, it has an opposite vertex there. Okay, and that reflection symmetry through the center then allows us to double all the existing rotations, so we get sort of non-orientation preserving analogs of all of the rotations by composing them with such a reflection. So we just have to multiply by 2. And that is 120. Okay, now there's still some question as to what the structure of these groups is. This is a pretty interesting question, and maybe I'll just say it for this one here and let you think about these ones here. You can easily look it up. So if we have let's say use a dodecahedron here, okay? If we have a dodecahedron like this, so if we have a dodecahedron like this, how can you think about these rotations in terms of what kind of a group it is? Well, it turns out that this group is the alternating group on 5 things. So this is a group that in mathematics is called A5. It's the alternating group. Alternating group. Okay, what is the alternating group? So remember the way I defined the symmetric group. So I defined the symmetric group as a group of n by n permutation matrices. Okay. Now when you take that position, a permutation matrix has determinant either plus or minus 1. And not too hard to see that half of them have determinant plus 1 and half of them have determinant minus 1. And if we just look at the things which have determinant plus 1, then that's going to be a subgroup. In other words, that's going to be closed under multiplication because the determinant has the property that the determinant of A times the determinant of B is the determinant of AB. So if you multiply 2 things that have determinant 1, you're going to get another matrix with determinant 1. So that means that subset, that half of the symmetric group consisting of even elements and some ones with plus 1 determinant, they are going to form a subgroup, and that's the alternating group. Okay. And it's actually quite an important group. This is the smallest simple group, non-abelian simple group. So this is in group theory, this group is actually quite important. And you might think, well, where's the 5? Of course, there's 5s because we've got regular pentagons. But the 5s can be thought of in a number of ways. But one way of thinking about that is to find some cubes inside this thing. So how do I get a cube? If I take, I think like this, yeah. If I take this side of this side here, and I take these 2 there, and I take corresponding these 2 there, right? So do those 4 points look like they're forming a square? Okay, and if I sort of go down here, correspondingly, there's 4 more points forming a square. So inside here, I actually have a cube. Okay, it's a cube. So it turns out that there's 5 such cubes. So if, for example, that one I just showed you, but there's also one like this. So every one of these vertices ends up being in a couple of different cubes, and there's 5 such cubes. And if you actually rotate the solid using one of these rigid motions, those 5 cubes are going to permute. And so that's one way of thinking about where the alternating group comes from. Okay, so very, very interesting. These numbers here are perhaps particularly important. 24, 48, 120. We'll probably be meeting them in various places. And this is a great sort of starting point to ask, well, what happens in higher dimensions? This is a very interesting question that was settled by Ludwig Schläfli in the middle of the 19th century. And the answer is quite remarkable and turns out to have beautiful connections with this entire story that we're developing towards the Standard Model and related exceptional structures. So I'll tell you all about that the next time.